Morning, everyone. So I'd like to thank Frankwell and thank Mark for having me here, and also for making my book available to all of you. So hopefully you'll have a chance to look at that. And it's written for general audience. I know a lot of people here are more technical, but even my technical friends have found that they don't know all of the different kinds of AI, and so hopefully you'll find something interesting in the book. And Mark already introduced me, and so hopefully many of you know me from Microprocessor Report. And now I've started a new career as an author, so I'm here to thank you. Here to talk about that. So I'm going to, kind of following what I talk about in my book, I'm going to present, of course, a much faster tutorial on neural networks. And some of you probably already know this, but then diving into how these neural networks are implemented in hardware, and then talk about how the chips actually implement this hardware acceleration, and finally end with some future trends. So everybody's talking about these large language models and the chatbots that implement them. And so these models are based on neural networks. And if you're looking at a large language model, for example, you have a neural network that takes in a sequence of words which are loaded in the context window. And then all of those words go into the neural network, and it applies these mathematical techniques to predict what the next word is going to be in this sequence of words based on the patterns that it's learned during the training process. And I explain all this in a lot more detail in the book, so I'm just going very quickly here. But in order to produce what you guys see when you use a chatbot, then the neural network takes your inquiry, produces the first word in the response. That word is added back into the context window. Then you run the neural network again to generate the second word in the response. And then you keep doing this until you have something that looks like a complete response to your query. So a few things I want to stress here is that when this is a purely mathematical process, and that the model only generates an output when you ask it to generate an output. So when people are talking about neural networks becoming conscious, thinking for themselves, doing things, there's no consciousness here. And this model only runs when you tell it to run. So it does the chatbot job, but if you're worried about Skynet taking over the world, that's really not what this technology is ever going to do. So as I said, these neural networks are based on mathematical equations. This is the fundamental equation here that's used. And the neural network, as you can see from this graphical representation, consists of a series of neurons. Each neuron takes a set of inputs, applies this mathematical equation, and then produces a single output, which is routed to the next set of neurons in the neural network. So each of these connections, the arrows in the diagram, has a weight value assigned to it. So how important is this input to the value of the neuron in question? And so you can think about the neuron as calculating a weighted combination or a weighted average of the input values, and in order to produce its output. And so the equation is very simple. You just take the first input, you multiply it by the weight. You take the second input, multiply it by a different weight, and so on, and add them all up to get the output. Now, one interesting aspect of this then is that this process is deterministic. That is, for any given set of inputs, you're always going to get the same output of the neuron. And therefore, when you look at the neural network as a whole, anytime you give the neural network the same set of inputs, you always get the same output. So it's a very reliable process. And also, one of the things to note about this graph is that typically these neurons are fully connected, meaning that each neuron takes input from every neuron in the previous layer. And I'll talk about how this affects the computation later on, but it's a convenient issue. So this diagram is obviously a very simple neural network. If you want to actually build interesting neural networks, they have to be much larger than this, of course. The first layer of neurons, the orange ones, are the inputs. So the more inputs you have to the neural network, the more of these input neurons you need. So if you have an LLM that takes as a context up to 1 million words, then you have to have 1 million input nodes into your network. So it gets wider very quickly, and you have to be able to handle all of those inputs. If you have, alternatively, maybe you have an image recognition network, and you want to take an image that has 1 megapixels. Well, each of those pixels has to have its own input. So again, with images, you can get very wide networks. And then if you want to perform more calculations in the middle of the network in order to produce your output, then you need more layers going deeper. So now you have a wider network, and then you have a deeper network. You can kind of say, well, the deeper the network, the smarter it is. If you want to be more technically accurate, you would say, well, you want to improve the output accuracy. So for example, in the word prediction, that you're more often predicting the correct word in the sequence, or in an image model, you're more accurately predicting, or you're more accurately labeling what the object in the image is. So the deeper the model, the better it gets, which is why companies have been building deeper and deeper, wider and wider networks. And now we see neural networks with thousands of layers, with billions of neurons, with trillions of connections between the neurons. And remember, in the equation, each of those connections has its own multiplication and its term in the equation. So now the number of computations you need to compute in order to produce one output becomes in the trillions. And the other issue with these larger networks is that you have to store these weights somewhere. If you have 1 trillion connections, you have 1 trillion weights. So that could be 1 terabyte of memory just to store the weight values. And so that becomes a limiting factor as well. So when you start trying to perform these neural networks in a chip, and you're looking at doing trillions of computations, it's going to take forever to do that in a normal CPU, where you have to fetch an instruction and do a multiply, and fetch another instruction and do another multiply. And so what we've seen is the deployment of vector units, which Francois mentioned, in order to do more computations in parallel. But even that approach isn't up to these large state-of-the-art networks with trillions of computations. So now the typical implementation for high-end AI chips is something called a matrix unit. And this is just an array of multiply accumulate units, which you might be familiar with. And if you take the neural network equation, it maps neatly onto this array. So what happens here is that each box is doing one term from the equation. So the top box, upper left, could do n1 times w1. And then the next box down would do the second term of the equation as the sums flow down, and the third term, and so on. So each column calculates the output of a single neuron. Now, when I mentioned that each neuron in a layer is fully connected, so it takes all of the inputs from the previous layer. So every neuron in that layer has the same set of inputs. So those inputs then flow across the network, across this array, And so the second column calculates the output of the second neuron in the layer, and each column then calculates a different neuron. So now, within this single matrix unit, you can calculate the output of multiple neurons in parallel without any programmable input. You set up the inputs, you set up the weight values, everything just chunks right through here. And so this is the most efficient piece of structure of hardware that is been designed to accelerate these neural networks in hardware. And so what we see is all of the leading chips that are focused on AI are using this kind of matrix unit, often called a tensor core. Nvidia, for example, uses the smaller versions of these tensor cores that can do 512 MAC operations every cycle. And then it puts 1,000 of them on the latest chip. And so if you think of the diagram I just showed, 512 MAC operations per second, that would be 16 by 32, array of these MAC units. And then Google uses the matrix units as well, but they have a slightly different approach, which is to make them as big as possible. So the latest Google TPU has only 2 tensor cores, but they're extremely large, 512,000 MAC units, which would be an array of 512 by 1024, and then just 2 of those on the chip. And the reason is that the larger the array, the more efficient it is to do very large models. So when Google is doing its very large language models, they are most efficient on this type of design. What Nvidia is doing, however, is saying, okay, well, we have to deal with a lot of different customers with maybe they have big models, maybe they have smaller models. So it's more flexible to use smaller cores, and then we can map whatever you need to onto these cores. So because of the different customers and the different workloads, NVIDIA's chosen a different approach, but fundamentally they're both based on these same matrix units. And we also see chips that are going into smartphones, chips that are going into PCs, even in embedded applications using these kind of matrix units, often smaller ones for those kind of chips, but the same structure to efficiently execute these neural networks in hardware. Now, memory is an important part of this as well. I mentioned earlier that state-of-the-art network could have a terabyte of weight values. And when you look at the matrix unit, you have to make sure that you can feed enough operands into the matrix unit in order to keep all of those weight values operating. And so you can end up needing several terabytes per second of memory bandwidth in order to feed one of these enormous matrix units. And even if you break that down into smaller matrix units, however much throughput you want to have in your chip, you're going to need to feed this data in at a very high rate. And so when you look at chips like the Nvidia GPUs, the DRAM is not fast enough to sustain this kind of bandwidth. So these very high-end AI chips are using high bandwidth memory, HBM. And then because of the HBM, you have to use silicon substrates, which adds even more cost. And everything gets very expensive because of this bandwidth requirement. Even if you're using a smaller kind of on-chip matrix unit to do smaller models on chip, you would still need enough memory bandwidth to sustain the throughput of that unit. So oftentimes you see dedicated fast SRAM blocks connected to these units in order to make sure that the bandwidth requirement is sustained. And of course, if you don't have enough memory, then you're never going to reach your peak performance in one of these units. Another aspect of this is the software. So that's always a crucial part of any deployment. The nice thing about neural networks is that they are developed using these standard frameworks, frameworks like PyTorch or TensorFlow. So there's a architecture-neutral way of developing and expressing these neural networks. And so the neural network sits on top of the framework. The hardware vendor typically supplies some kind of driver as an interface to translate from what the framework is producing into instructions that the chip can execute. Now, the problem, the first problem here is that if you're creating a new chip to run an AI model, you need to create this driver. And the drivers have hundreds of different functions, and even if you support all of them, you have to make sure that the driver is optimized for performance, because otherwise you're going to get much better performance on somebody else's chip. And so there's a lot of software development that goes into the driver, as well as the hardware development to create a new AI chip. And the second problem is that the frameworks don't actually support all of the functions that the neural network developers need, particularly because AI is still a fairly young technology. And so the developers are always coming up with new ideas of functions that they want to implement. And so they have to bypass the framework itself. And because most of these developers are using Nvidia chips, what they use to build their custom functions is CUDA. So CUDA is an Nvidia software that runs on Nvidia GPUs. And of course, Nvidia doesn't let anybody else use CUDA. So now if you say, okay, well, I have a chip, but it doesn't support CUDA, you have to work with the customer to implement whatever custom functions they have and port them over to your architecture. So now there's additional friction there. So this is one of the reasons why NVIDIA has been so dominant in the AI business, is that the customers, once they start using CUDA, are kind of locked in, even though the framework itself is architecture neutral. So it's something that needs to be overcome. So now I'm going to talk about some more trends in this area. When for a while at my conference every year, I would put up this chart and show how neural network size was increasing at this dramatic rate of 40x per year. And that went on for a few years until we got up to about 1 trillion parameters per model. And then, since then, we've really seen it flatline. And there's a few reasons for this. One is that by the time we got to GPT-4, OpenAI was basically scraping every page it could find off of the internet and using it to train their model. So once we've kind of gone through the entire internet, it's like, where do we get more data? And so it's been difficult to find enough data to train. If you wanted to train a 5 trillion parameter or 10 trillion parameter model, where would you get all the training data? So that's been holding things back. And then in order to make these models bigger, you would also have to pay the cost of training them. The bigger the model, the more computations it requires, the more cost to do the computations. And then if you're training your model on the entire internet, you have to run that model many, many, many times, and that drives the cost up to $100 million or more to train one of these state-of-the-art models. And that's a trillion parameter model. If you wanted to go again to 5 trillion, 10 trillion parameters, you can imagine what the cost is going to look like, and it becomes difficult to afford. And the same thing applies when you deploy the model. Now, as AI is becoming very popular and more people are using AI every day, the cost to a company like OpenAI or Google is the cost of running these models over and over and over again. And so in order to be profitable, that cost has to match up with the revenue stream. And that's limited these companies from trying to deploy bigger models because they're just going to end up losing more money because of the cost of running the bigger model. Now, one company that has kind of bucked this trend is XAI. Grok 3 is really one of the few models that's been in the 2 to 3 trillion parameters. Grok 4 supposedly was a little bit smaller, and then Grok 5, which is not yet released, Elon Musk has been saying has 6 trillion parameters. So that would really start to change the shape of this curve. But from what we've been hearing, other companies are still trying to stick to the smaller models in order to be more profitable, or I guess less unprofitable, shall we say. So because of these economic constraints, then in order to be profitable, then the cost has to be matched with the revenue. And in order to improve the model, in order to make the model bigger, you have to be able to do that at the same cost. And so the one way to do that is to improve the performance per dollar of executing a model on the hardware. So hardware vendors are really trying to deliver this better performance per dollar because that's what the customers are demanding. We want bigger models, but we want to be able to do them in the same cost envelope as the existing models. And so there's this big focus on efficiency right now. Electricity is another issue, and so performance per watt is a crucial metric, and it sort of all rolls back into what is the total cost of ownership of the AI chip, because electricity is a part of that, but improving the performance per watt is also something that the customer is going to be very interested in. So really we're looking at new ways to design the microarchitecture and the architecture of these chips in order to improve the efficiency per watt, the efficiency per dollar. And we're not getting much help from transistor manufacturing. I mean, the new 2 nanometer chips are really not that much more efficient than the 3 nanometer chips or the 4 nanometer chips. So, where we used to kind of get a free ride from Moore's Law, that seems to be kind of over. And so, again, the focus is really on the chip design itself and how can we make these chips more efficient. Changing gears a little bit, different trend is agents. I just wanted to talk briefly about kind of the hot new thing in AI is these agents. So going beyond just an LLM or a chatbot, but that they can tell you things, and the agents are actually able to do specific tasks, but using the same conversational interface as a chatbot. So we've seen agents being deployed to do support, customer support kinds of things, to do administrative tasks. You could maybe use them to book an airline ticket or file an insurance claim, something like that. So instead of just telling you what to do, it actually puts everything together for you. And so when you build these agents, of course, you still need the AI, you still need the LLM, but you have a lot of traditional software as well. So this is kind of changing the way the computation goes from just these matrix arrays to CPUs as well. And I'm running out of time, so I'm going to just skip to the last slide. Here at a RISC-V event, so I wanted to talk a little bit about RISC-V. And so as I was saying then, with these agents, we're seeing more demand for traditional CPUs and then the software lock-in I talked about, the the fact that you're not tied into a specific architecture, so you can use RISC-V, ARM, x86. I think any architecture can fill that role, and the efficiency, as I mentioned, is really paramount. So I think the challenge for RISC-V vendors here is to bring the efficiency of RISC-V, the flexibility of RISC-V in the instruction set, to use that to more efficiently execute AI models in the hardware. And I think there's a lot of different implementations of AI I mentioned in my book. So so I think you can start it with smaller models. You don't necessarily have to go head-to-head with Nvidia in the data centers. And so I think there are definitely opportunities for RISC-V, in the AI market. And probably the best place to start is with these smaller models, and then eventually get up to a bigger role in the market. So that's what I've got for you today. Thank you for your attention.